Hi everyone, in this video I'm going to show you a game I made in Python. The game is called PyHill. I made this game for my 11th grade computer science project. It's an endless 2D driving game where the objective is to drive as far as possible, set new records and beat other players. What makes this project interesting is how everything works internally. First, let's talk about the architecture of the game. The game is written entirely in Python. I used the Pygame library for graphics and input handling. I also integrated the Pymunk library for physics simulation and collision detection. But these two libraries do not automatically work together, so I had to structure the game loop carefully. As you can see, each frame has physics updates such as the position of the car, the force applied, its angular momentum, and its angular speed. There are also collision checks happening to check if the vehicle is in the air or not. Also, there are game state updates happening throughout, which track the current distance covered, coins collected, and flips performed. Finally, rendering happens where the graphics are drawn to the screen and text is laid out. All of these run in real time. Next, let's talk about the players and data handling. One of the important features of this game is that it supports multiple players. You can see here that each player has a saved profile, high scores, and stored progress. To handle this data, the game reads and writes structured data using JSON. When a run ends, the score updates, the leaderboard resorts, and the file is written instantly. This ensures persistent storage. Now, let's look at the vehicle physics in the game. Each vehicle is not only visually different, it also behaves entirely differently. Their mass, friction, torque, and acceleration are all configured separately inside the physics engine. The movement is physics-driven, which means that the vehicle acts like it would in real life. Gravity affects them dynamically, the rotation is calculated in real time, and momentum carries forward naturally. Next, let's look at the terrain. The terrain is procedurally generated, meaning it is not predefined, so it can go on for infinitely long. The hills are generated using a mathematical sine function which is defined as y equal to a sine bx. The height and spacing of these hills are randomized. Every run generates a different track, which means it's always a unique experience. To keep performance stable, old terrain tiles are deleted and new ones are generated ahead. This prevents memory overflow. Now, let's look at some core game mechanics. Firstly, there are coins. The player earns points for the number of coins collected. Coins are placed dynamically and randomly across the terrain. When a player reaches a coin, a collision detection checks if the body collides with the coin's hitbox. There is also a fuel mechanic. The player has a set amount of fuel which must be managed efficiently. The fuel keeps on decreasing according to the throttle input of the player. The player can refuel using fuel cans which spawn randomly. If fuel reaches zero, the run ends. To add some thrill to the game, I have added bonus points for performing flips. For each front or back flip performed, the player gets 1000 coins. Flip detection works by tracking rotation angle over time. Let's now take a look at the performance of the game. Running these many calculations and physics updates are compute intensive. To improve efficiency and performance, I've used many optimization techniques. Objects behind the player are removed. Unused physics bodies are deallocated and rendering only happens for visible elements. This prevents lag during long runs. The game also has a leaderboard mechanic. All the runs are stored. After every game, the scores are compared, sorted, and updated. The leaderboard dynamically reflects the best runs. This lets players compete against each other to be at the top. Let's now look at some challenges I faced while building this game. Integrating real-time physics was the hardest. Balancing stability, realism, and playability took multiple iterations. Another challenge was procedural terrain smoothing. Random hills can become unplayable, so I had to implement constraints to limit extreme slopes and make the terrain drivable. In conclusion, I was able to combine all the above features into a complete playable game. There were many features that I wanted to add to make this game more advanced. However, I was constrained by the project requirements, which forced me to use Python and Pygame. If I were able to use an advanced game engine such as Unreal Engine 5, I would have been able to make much more featureful and advanced game. The entire source code for this project can be found on my GitHub page linked here. That's all for this video. Thanks for watching.